Hello everyone, welcome back to the Tensile Lab for our Polymers Lab. So we are reaching near the end of the semester and we are going to be testing some kind of new materials, polymers that we have not talked about previously so far this semester. Hopefully you have watched the lecture so you understand the kind of basic gist of polymers. They are long chains of molecules bound together through covalent bonds, and these molecules can either be held together to each other through secondary bonding, things like van der Waals or hydrogen bonding that's relatively weak and allows them to slide and deform quite a bit, or they can also be held together by cross-links, which are covalent bonds that jump from chain to chain, and those, depending on how much cross-linking there is, can either allow for some amount of elastic and no plastic, or no elastic and no plastic deformation. So in this lab, we're going to test two different kinds of plastics with varying amounts of crystallinity. We've mentioned that you can have semi-crystalline polymers where the chains will align themselves in small regions of the material, which make it stronger and more dense. So we have LDPE, low density polyethylene here. We have HDPE, high density polyethylene here. If you put them side by side, you can see the low density is a little bit clearer because it is lower density. And we have some cast epoxy, which is very hard and very brittle, heavily cross-linked, and we have polyurethane, which is very amorphous and very elastic, but still cross-linked. So at the end of the day, still not very plastic. Small amounts of plastic deformation are possible. So for LDPE and HDPE, we're going to test them at two different strain rates, 500 millimeters per minute and 50 millimeters per minute. And epoxy and polyurethane, we're just going to test and compare them at a single strain rate. Epoxy at 10 millimeters per minute and polyurethane at 50 millimeters per minute. So we are also going to do a stress relaxation test. The plastic materials have the ability to flow to relieve internal stress, so we're going to pull them to a set stress and record as their stress drops over time. So, all right, let's go to the tensile test frame and let's start doing these tests. So we're going to start off doing our stress relaxation tests because they are the quickest and frankly the least exciting, so we'll end with the more exciting stuff. So we're using the Blue Hill software. You've used it before, so we need to set a strain rate, and for stress relaxation we're going to take this sample, we're going to pull it until it is loaded a set amount for HDPE that is 1 kilonewton, and then we are going to record the stress as it drops over time. So gripping the HDPE, and I've already set the hold load at 1 kilonewton on the software here, and we're just going to go ahead so I'm going to preload it a tiny amount and reset the gauge length, and I'm going to go ahead and start the test, and we'll do this for 1 minute. So you can hopefully see we have our peak here, and then it levels, it decreases over time as our polymer chains are allowed to flow. They will flow towards the edges, or they will plastically deform in order to relieve the internal applied stress. So you can't really read these numbers, I'm sorry, but we went from 1 kilonewton initial load. When we stopped, we were right at about 600 newtons. So we dropped about 40% over time. And it's actually still dropping even though the test is stopped. All right, so we're going to take this sample out. Okay, we're going to put in the LDPE sample. LDPE has a lower yield stress, so instead of doing one kilonewton as our set load, we are going to do 0.4 kilonewtons, so 400 newtons. Okay. Again, we'll give it only so a minor load initially, and we'll go ahead and get started. Okay, so we stopped it. We went from 0.4 at the left side here all the way to the bottom. We got to a little bit less than 0.3, maybe 280 newtons. So we went from 400 newtons to 280. So we dropped still quite a bit. Okay, so those were our stress relaxation. Now we will go to the other testing mode, which is just the tensile testing mode. I'm going to take the sample out. Okay. And now we will test our LDPE, HDPE at 50 millimeters per minute, 500 millimeters per minute, and then our epoxy and our polyurethane elastomer. So we're going to go ahead and set those guys in there. So we'll start with HDPE at 50 millimeters per minute. Okay, let's go ahead and get started. You can hopefully see we have our load that increases up to about 2.5 kilonewtons. You can also maybe read it here. Then we kind of get this drop down in the stress, and if you can hopefully see, we're getting some necking or constriction for our HDPE sample. I'm going to move in to see it a little better. can see that our load actually levels off. It's increasing maybe a tiny bit. Actually, it's remaining relatively constant, as you can see by the value here. But we're just getting continued extension with a pretty consistent load. Hopefully, I don't know if you can read this, but right now we're at 128, 129 millimeters of extension for our HDPE. You can imagine compared to our steel samples, which, you know, we're at 10 millimeters maybe for the best samples. We're, you know, nearing 15 times that extension value. We wanted to look at our sample. See, we start to get some drop off here. And even though it hasn't completely detached, the system has decided our part failed right there at the top. So we got up to 195 millimeters of extension on our sample. So let's take out the sample. So here is our bar. And it's actually a little warm right here. A little bit of friction in alignment of those polymer chains. So now I have loaded another HDPE sample in the grips, and this time we're going to pull it at 500 millimeters per minute, so 10 times faster. And we will see the effect this has on both the applied stress and the ductility of our HDPE sample. So we got to about 2.5 kilonewtons on the first one, and an extension of around 200 millimeters. So 500 millimeters per minute. Here we go. So there's our full test. You see our extension. We stopped at 24 and a half. Our max load was a little bit higher, about 2.7 kilonewtons, but yeah, there's our whole thing, really fast. And here's our sample. So quite a bit different at higher strain rates. All right, now we're going to do LDPE at 50 millimeters per minute. So lower density, I wonder what will happen with the ductility and the stress. Let's get started. We have kind of a similar initial. We're not getting that big peak drop down that we saw with HDPE. Our maximum load is around 0.95, so almost, we'll say around 40% of HDPE, but we still get this kind of little drop down. Okay, so not quite as much ductility as I expected, but we have a extension of 92 millimeters, so about half of what we saw in our HDPE sample. And here is our sample. And you might be able to notice on the edges here, our sample actually is clear. You can see through it. So the reason this happens is because it's already relatively low density. So as we pull it apart, all of our polymer chains that are kind of randomly bunched up and squished become all aligned in the same axis. So they become crystalline. And when they become crystalline, their order and their spacing is just enough for light to transmit through. So we go from this kind of not translucent, this opaque, kind of frosted looking to this nice clear, which is pretty cool. Okay. Our last one, LDPE, 500 millimeters per minute. So let's see what happens at this really high strain rate for LDPE. Well, there you go. So you might see, you probably can't see it, but our maximum load is around 1.05 kilonewtons, so a little bit higher. But our ductility, our extension, ended at, right before it broke, around 55 millimeters. So we basically cut our ductility in half for this. So but you can maybe still see we still got the clear effect. It just happened a lot faster. Okay, so for the cross-linked, we're going to start with the epoxy sample. This is hard, so it's extremely cross-linked. So we'll see how it happens when we pull it at 10 millimeters per minute. Okay, here we go. Okay, that was pretty fun. The epoxy likes to pop. So if you look, we basically got all plastic deformation. We didn't have any of this kind of flattening of our curve, except in the beginning when it looks like it maybe slipped a little bit. But we had a maximum load of around, I don't know, 3.75 kilonewtons, so higher than our HDPE, but our extension was only 4 millimeters. So way worse on ductility for slightly stronger. And similarly, we don't, or I guess dissimilarly, we don't have a ductile fracture at all. This is very much a brittle type fracture with harder edges. No constriction, no cross-sectional area change, just straight up explosion. So our last sample is polyurethane. It's this guy, you can see, it's nice and floppy. This is cross-linked, but it is extremely amorphous and it is lightly cross-linked, which means it should have lots of elastic deformation, stretching, but once it breaks, it should be a brittle failure with a kind of sharp edge, and it should return to almost its entire original shape. So it should be almost all recoverable. So what we're going to do is at 50 millimeters per minute, I'm going to have to babysit this one and kind of continue to tighten the grips because it will slip out. But let's go ahead and load this one. Okay, let's get started on this one. Polyurethane, 50 millimeters per minute. So the test is going. You can see our load is very, very small, 0.1, 100 newtons to actually pull our sample apart. It is going up, but pretty low loads. So you can maybe see already at about 70 millimeters of extension, but our max load is still 0.183 kilonewtons, so 180 newtons. A closer look, you can see it's really stretchy. So our amorphous chains are becoming elongated and stretched out, but we haven't reached where the cross links are stopping tension, plastic deformation from happening. We're still inelastic. And our forces, if you want to look, you're all the way up to 0.23 kilonewtons and 140 millimeters of extension. So already much greater than our LDPE. Not quite at HDPE at 50 millimeters per minute. That was around 200. So just to check, 196, 197, 200 millimeters of extension, with still a force of only 0.26 kilonewtons. Three 325 kilonewton or 325 millimeters with 0.3. These little spikes are where I was tightening the grips, so not a function of the material, but almost 350 millimeters of extension. From this started at about 50 millimeters. If you see it. You can see at the grips, it's really stretching right here to slide out. So you need to keep pulling on it. We are very close to reaching the top of the test frame. And now we are at an extension of 400 millimeters. Still a load of only 0.32 kilonewtons. So we started at 50, so almost 8 times longer, 800% elastic deformation. And it broke. So it broke at a grand total. Let's stop the test. Appears it broke at a grand total of around, it ran for a little bit longer. So around 420 millimeters of extension. And after all that pulling, all that stretching, our bar is almost exactly the same length that it was when we put it in there. And our fracture surface, that's a ductile fracture any way you slice it. That's a nearly perfect flat ductile fracture. So as soon as the amorphous chains got stretched enough where the crosslinks were the main thing holding it together, the crosslinks failed, and then the whole thing failed. So we got our nice brittle fracture surface, and maybe, I don't know, very, very little plastic deformation, maybe a tiny bit, but this is pretty close to what it was when we put it in there. It might be 10 millimeters longer. Okay, that is the Polymers lab. So we have seen the effect of strain rate and polymer crystallinity when comparing LDPE and HDPE. We have seen the effect of cross-linking, comparing a heavily cross-linked epoxy to a very lightly cross-linked elastomer, both of which though experience brittle fracture and little to zero plastic deformation, but our elastomer had quite a lot of elastic deformation. So that's the lab. The data will be up, and thanks for watching. I'll see you next week.